Alright, so we're going to look at some set theory in this chapter. And a set is a collection of elements or members. We usually call it the elements of a set. And this chapter is designed to sort of get you thinking about ideas of categorization and why that can be important, and specifically in real-world thinking. So we're going to start with just the idea of a set. A set is a collection of elements. It could be anything. With the notation, we usually say a set, and we can call it any letter. I'll call it start with S, is, and then you do these squiggly brackets and put things in it. So maybe A, B, C, D, E is my set. Alright? Or maybe I say A is a set or B is a set. You can use whatever letter you want. So you can have sets of letters. You could have sets of numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. I'll call this one set 1 and this set 2. You can have sets of states. You can have sets of anything. All right. So a set is just a collection of elements or objects. Now we're going to look at the cardinality of sets, and what we mean is the size of the set. So we'll be interested in, we denote it with an N of my set S. So the cardinality of set S is just the number of elements in the set. So set 1, you can see 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 elements in that set. The size of set 2, or the cardinality of set 2, is 5. Alright? I want you to push pause and try to find the cardinality of these two sets. So find the cardinality of A and cardinality of B. It shouldn't take you more than a few seconds to find that out. Alright, so the cardinality of A, and this is the notation, right? Size of A is 4. The number of elements in B, which is the cardinality of B, is 6. Right? And all I'm doing is just counting the number of elements in B, alright, or in A, respectively. Like I said, the importance of sets is we're going to look at classification systems, alright? And it's very important that you can understand when people are talking about one thing being inside of another, or one set of objects and the other set of objects, their overlap, that we can kind of understand what's going on. Alright, so it's mostly important in understanding classification systems, and we'll see that in the later chapters. A lot of the things that we're going to talk about in probability, a lot of the things that you could see in logic, a lot of the things you can see in graph theory, actually boil down to set ideas, so ideas of sets. Now I want to say something about sets, equality versus equivalence. Alright? Now, when I say two sets are equal, that means they have exactly the same elements. So let me give you an example of equal sets. If I let A be the set 1, 2, 3, and I let B be the set 1, 2, 3, then A is equal to B. Alright, in this case. So in this case, A is equal to B. They have to have the exact same elements. Sets are equivalent if they have the same number of elements. So notice that if they're equal, then by definition they have to have the same exact number of elements. So if two sets are equal, then they have to be equivalent. However, the reverse is not true. let's take a set C. We'll call it, let me call it, let's do states. Let's call it Michigan, Illinois, Ohio. All right? So set C is a set of states. Now, the cardinality of A is equal to the cardinality of C. However, the sets themselves are not equal. Write that. All right. So A and B are equal. A and C are equivalent, but not equal. A and B are, by the way, equivalent. So obviously, cardinality of A is the same as the cardinality of B. But, so these are equal. A and B are equal. A and C are equivalent, but not equal. Now, there's a few special types of sets that we're going to look at. And one of those is the empty set. That's the set containing no elements. Now, you generally think of a set being denoted this way. Okay? So if we contain no elements, then we could just write out, brackets on each side with nothing in between. So just don't put anything in there. But we usually denote the empty set as like a big O with a line through it. Now notice if it doesn't contain any elements, the cardinality is 0. All right? So the cardinality of the empty set is 0. Now let me just take a side note, because some people get confused on this, the set containing no elements versus the set containing 0. Okay? When I say the empty set, I am meaning the set containing nothing. Cardinality of the empty set is 0. Now if I have the set containing 0, we'll call that, let me not do it that way. Let me call that Z, just for, alright, that's not standard notation, but let's just call it for right now Z. So the cardinality of Z is 1. Okay? So the set containing nothing is very much different than the set containing 0. Okay, and we have to sort of logically understand that. 0 is an option in a lot of cases. Okay? Oftentimes, people will say and do some logical explanation of something and say, well, we don't have any option. Well, there's often one option, but it's trivial. So, the thing, again, it's understandable, but we shouldn't get these confused. The empty set contains nothing, so its cardinality is 0. But the set containing 0 actually contains one element, so the cardinality is 1. Now the other important set, or at least one of the other important sets, probably the most important set, is the universal set. Okay? A lot of times this is denoted by a U. So the universal set is the set that contains all the elements for a specific scenario. So, for instance, there may be a scenario where our universe is just the numbers 1 through 10. So that's the only elements that I really want to be concerned with. Maybe somebody else's universe is the set containing all letters of the alphabet. I'll just write letters of alphabet. maybe another set somebody else is concerned with, the states, 50 states in the United States. All right. So there's a lot of different universes out there. And what's important to know is that if we're in a certain universe, if our only elements are the sets are the numbers 1 through 10, the counting numbers 1 through 10, then that sort of defines how we're logically thinking about something. All right? And it's important to know when we're talking what the universe is. All right? Now, so far, all of the sets that I've put up are finite. Okay? That means they have a specific number of objects. Like we said, the numbers 1 through 10. I'm just going to write the numbers 1 through 5 here. So we have the numbers 1 through 5. Or we had Michigan, Illinois, and Ohio as my examples there. So in other words, the cardinality here is just a specific number. Now there are infinite sets of things. Like if I said take all of the counting numbers. 1, 2, 3, and then I go on forever. Okay? Or if I take all real numbers. Those are infinite too. All right? There's no end to the real numbers. There's no end to the counting numbers. And we're going to look at some of the interesting things that happen with infinite sets in the last section of this chapter. Finite sets we're going to deal with for the most part, but I will say some really odd and interesting things happen with infinite sets.